Could someone that is online confirm that they can hear me?
No.
Oh, thank you, Vanessa.
Fernanda, can you try again to say something, please?
Sure. Can you hear me now? Hi, hello.
Yeah, ahí estamos. Yeah, now it's working.
Oh, great.
Okay, I will first introduce you to the audience in Spanish, and then I will give you the microphone to speak. Disculpas por estos minutos de atraso, tuvimos problemas técnicos, pero ya estamos con nuestra siguiente presentadora en línea. La siguiente contribución tiene como título Variable Selection in High Dimensional Linear Mixed Effects Models y está a cargo de la doctora Fernanda Lang Schumacher. Ella es doctora y máster en estadística por la Universidad Estatal de Campinas y licenciada en estadística por la Universidad Estatal de Maringá en Brasil. Se desempeña como profesora en la Universidad de Ohio State, trabaja con modelos de regresión mixtos y en los contextos de series temporales y datos longitudinales, principalmente desde un punto de vista frecuentista. La mayor parte de su trabajo está disponible como paquetes de R de código abierto, lo que facilita el uso de modelos flexibles en aplicaciones. El principal de investigación de la doctora Schumacher ha sido el desarrollo de modelos estadísticos sólidos que puedan adaptarse a características específicas que se encuentran con frecuencia en las aplicaciones, como valores atípicos, asimetría, dependencia del tiempo y censura. Vamos a comenzar entonces. Fernanda, the floor is yours. You have 15 minutes for your presentation, and thank you very much for your time and waiting time.
Of course. Good morning, everyone. It's a pleasure to be here with you today, and thank you for the very nice introduction. Well, I do apologize for not being there in person. I wanted to go, but I couldn't at this time of the year, unfortunately. But I'll do that next time for sure. And also, I do apologize for not speaking Spanish. I am from Brazil, as you could guess by the universities I studied in. And my primary language is Portuguese, and I can understand Spanish well, but apparently Spanish speakers can't understand my Spanish, so English was safer. But feel free to ask questions in Spanish. I can usually understand them, and I'll let you know if I can't. So I'm gonna talk about variable selection in linear mixed models, and this work is in collaboration with Daniela Oliveira and Victor Lachos. Daniela is also from Brazil, and Victor is from Peru, but is working at UConn in the US now. Well, first, I'm not sure if everyone is familiar with mixed models and longitudinal data or repeated measurements data in general. So I want to get started by a 1-minute introduction to mixed models. And basically, in the context of longitudinal data, what we usually have is something like this plot here. When we follow a few subjects or sampling units over time. So we have repeated measures for different times in the same subject. However, we're still interested in estimate the populational effect. So the general average over all subjects effect that is represented in this plot by this black line here. But we need to account for the dependence, the dependence that comes from this repeated measurement. So in mixed models is a tool that we can use to handle this. It's not only useful for longitudinal data, we could have any kind of clusters. We can think about students within a classroom, or anything that is like nested, or that we can see like a natural cluster. Any kind of repeated measurement would work. We can use some model like that. And it is also particularly useful for missing data, which is also quite common, that we don't have the exact same number of observations for each subject or for each sampling unit. What these models do, why they're called mixed, because they have both fixed and random effects, and the fixed effects will be the parameters associated with the entire population. So this is the parameters that the whole population share. And the random effects will be an additional source of random variability that comes in the individual level, that comes from sampling these individuals at random from a population. So this is the way we can represent this as the model as an equation. So the traditional regression model would have something like this, like y equals to x beta, and in here we are adding an additional source of variability. So we are adding the b that are the random effects. And z here represents the design matrix corresponding to the random effects vector. But we also have the X matrix, that is the design matrix corresponding to the fixed effects. Now, as I mentioned, we have two sources of variability. We still have the random error at an observational level, but we have an additional source of variability that comes in the individual level. So we have two sources of variabilities. And this adds a lot of flexibility because we can accommodate this dependence that comes from the repeated measurements. But it also, as always, when we add flexibility, we need more assumptions. There is a trade-off there. And there's also is something else to consider. We could have, in this context, we could think of selection of variables in two settings. One would be in X and the other one would be in Z. So we can select both the variables from the design matrix of the fixed effects and from the matrix associated with the random effects. But in this work, we are focusing on the selection of variables in the fixed effects part. So we are just interested in selecting the variables that all the population share. And this work proposes to use the expectation maximization algorithm to solve problems of penalized maximum likelihood estimation. And we proposed an algorithm that is called YAM-LM-LASSO. And it combines the optimal, efficient estimation from GLMNet package that is designed to handle independent data. So it combines that with the mixing variable repeated measurement setting from mixed models. And it can be used in both settings with less variables than number of observations, but also in the setting with more variables than number of observations. And I will show you some results of how this worked, and it presented interesting, consistent results for the cases we considered. So how do we select variables? Similar to what we would see in a regression setting, what we do is adding a penalty term as a function of beta that is regulated by this parameter lambda. So we add this term, this penalty, to the log likelihood function, and this will also yield penalizing the complete data log likelihood function that we have in the EM algorithm. So we can write the complete penalized log likelihood function as this. This would be the kernel, the traditional log likelihood function from the mixed model I presented to you before by assuming normality. So this would be the part from the individual level, and this other part would be from the random effects. And we can, so what we propose is to penalize this function in order to enforce variable selection along with estimating the parameters. And I will show you briefly what the algorithm looks like. We first need to choose to fix for a fixed value of lambda of that regularization parameter. For a fixed value of lambda, we initialize it beta, sigma, and d. So sigma is the variance associated with the random error, and d is the matrix associated with the random effects. So we have more than one source of variability, we have more than one variance to estimate, and that's what's written here. So we initialize them like this, and this is just a L1 penalty for beta, because we are using a lasso penalty, but this could be any different penalty. It would work the same way. And then we specified at each step, we have a E and a M step, which is traditional from the EM algorithm. And in the E step, we compute these expectations that will have these expressions, where we transform, let's say it like that, the response variable by removing the effect of the random effect at each iteration. And we also use this transformation of lambda that have this this expression. And then in the M step, I'm sorry, someone mic is open. In the M step, we optimize, we compute the we maximize that complete data expression. I'm sorry, Michael, could you turn off your mic, please? Thank you. So in the maximization step, we compute this, we optimize that expression as a function of the parameters, and we'll have something like this, where for sigma and for d, we have closed forms, so we can iterate and compute this. And for beta, we have to minimize this function, where we have in here the penalty that we specified before, depending on this lambda that we are computing here. So we do have this general expression to maximize, but in here since we're using this depends, this is a function of y tilde. This is actually, we're removing the effect of the random effects. So the way, by doing that, we can actually use the GLM net package that is designed for independent variables. But by doing this iterative process, we can actually remove this effect at each iteration and use this already implemented tool. So this is this part, that this is the only expression that doesn't have a closed form. This is done by utilizing the GLM net package. And then we need to use some selection criteria to obtain the optimal value of the regulation parameter. And we do that using a grid of possible values. And after running this until a stopping criteria is reached, we return the estimates from the model. So that is the general idea of the algorithm. And now I'm gonna show you some results that we obtained. For comparison, we tried to use something that was established in the literature for variable selection in mixed models, which is not actually, there's not a lot of tools already available, but we compared this with the GLM-MLASSO. And we showed like for this case, beta 1 and beta 2 were originally truly different from 0, and the other parameters were 0. So this is the number of times, the percentage of times that each variable is selected. So in this table, we would expect that these first 2 lines are 0 because they are, sorry, the percentage of, sorry, I said it wrong. The percentage of times that the variable was excluded, not selected. So we would expect this to be 0 for the parameters truly different from 0, right? We would expect that these variables were always in the model. But for the other ones, we would expect that to be as close to 1 as possible, because we want, those were just noise, were not truly different from 0. So we would expect these to be not selected, to be excluded from the model as often as possible. And we could see that this, we actually were surprised that the GLM-MLASSO performed like this. We expected to be a little bit better. But if we compare the random, sorry, this is the proof of the mean squared error. If we compare them, they are not too different. So what it looks is that the GLM-MLASSO is not excluding some variables that have a very small coefficient. So the mean squared error is not too large, but it is not being able to remove or to exclude these noisy variables as often as we would expect. But the proposed algorithm, the EM-LM-LASSO, had some very exciting results for this setting. We had a lot of other settings, but I wanted to go ahead and share some applications. And I will start by showing the Framingham cholesterol data. This is a very known in literature data set. And we are looking into the widely available sample of 200 participants. And for this data set, we had the serum cholesterol, and we had these repeated measurements over time. So what we're proposing to do here is to use all the covariates that we have in the data set. There was the sex, the age, the time, and all possible interactions between that, but also thinking in a simulation and trying to see how well these algorithms would perform. We added some noise here. So we generated this X1, X2, and X3 are some noisy variables that we added just to add some difficulty. So this would be an example where we have less variables than number of observations, but we added these noisy variables that have coefficient 0, just to see, originally the coefficient is fixed at 0, just to see how these algorithms perform in this setting. So what I'm showing you here is what the E is from excluded and the I is from included. So again, comparing these two algorithms, we can see that the GLM-LASSO only excluded the last generated variable and included all the other variables, while the EM-LM-LASSO excluded a lot of variables. So it only included in the final model age, time, and the interaction between sex and time. All the other variables were excluded, including the 3 noisy variables. We also fitted a LME4 to this selected model. So only considering the variables that were selected, we fitted this LME4 model and compared the p-values just to have an idea of what decisions we would do if we were looking at a more standard, not penalized estimation, but a standard maximum likelihood estimation and inference, right, from this model. And we can see that for this reduced model where we only account for age, time, and sex and time, all variables were really significant, like all the p-values were very small. And while for the other model, the one selected by GLM Lasso, we have some significant variables, but we also have, for example, the sex, age, and time interaction doesn't seem to be significant, although it selected that. And also these two noisy variables that we expected not to be significant, right? Because they were generated independently from the response variable. So those are also not significant, although they were selected by this algorithm. And lastly, I want to show you an application on riboflavin. And this is in the context of genetics, so of trying to select genes that are important to explain the behavior of, for example, in this case, is the riboflavin production. And we use it, so this is really high dimensional data. We have much more variables than observations. And we are only using this reduced data set actually that contains the 100 more important variables to represent that. And we are also adding the time it is longitudinal, so it is repeated measured over time. And we are also accounting for the time here. But we want to select these genes in the model, and we have 100 of them and only 71 subjects. So this is correlation matrix between the covariates. And I know this is hard to see and to take much away from this, but what I want you to see is that we have several blocks of really correlated data. And so in addition to have more variables than observations, at least than independent units of observations, we also have very correlated covariates. So that would make the use of standard regressions or methods that don't account for this penalization impossible. But these algorithms can still handle, these proposals can still handle this kind of setting. So we have some negative correlations and some blocks of very high correlation. And this actually is emphasized because we have the gene expression is either -1, 0, or 1. So in a setting of a smallish sample, it's very likely that we'll have some variables that are identical to others, but we need to be able to account for that. And this is the results, the variables that were selected using GLM Lasso and using the EM-LM Lasso. And we also try to remove a little bit of this correlation by adding a function that find linear combos just to remove this correlation to see if it would improve the performance from GLM Lasso, but it didn't select. When we used that, it only selected the time as opposed to the EM-LM Lasso that actually selected some variables. I don't remember the specific number, but you can see there is like a reasonable number of genes that might be important to explain this variable. So this is also the mean squared prediction errors when we have fourfold cross-validation. So removing a fourth of the data, breaking this in four settings and comparing these results. We can also see that the C seems to be the best model between the best method between this based on these results. That is this EM-LM Lasso. without defined linear combination function. So I think I am on time here, but I just want to share some conclusions that this algorithm that was proposed using the EM algorithm seems to be performing well in several settings. And we want the next steps that we want now is to compare with an additional package that we recently found out about to see if the results are also comparable with this other method, this SPLM. And we are organizing these codes to distribute it in GitHub. These are some main references that I mentioned along the talk. And this is it. I'd like to thank you again for listening. And this is my contact information. I'd be happy to chat or to answer any questions that you might have later. Thank you all.
Thank you very much, Fernanda. Please, a round of applause. We are a little bit over time, estamos un poquito fuera de tiempo, but we still have like 2 minutes for questions. So I will ask the audience if they have questions and I can translate if it's necessary. ¿Alguna pregunta? A ver, then we have 2 questions. So we will go first to Oliver.
Hi, Fernanda.
Hi.
I
I can see you, so.
Okay, nice. I'm wondering if this estimation method, which is based on Lasso penalization, introduces bias in the estimation of the coefficients, because Lasso is very well known to introduce bias. I'm wondering that.
Right. Yeah, all the properties that I would expect all the properties from Lasso in the regression contest also happen here. So it can introduce some bias, but in some settings, for example, this riboflavin example that I gave you, there is really not other way. I mean, you can use other penalties, and that is for sure things that we are consider or planning on accounting in the future that might introduce less bias, that might penalize less the coefficients. But it might be useful in these really high dimensional settings. It might still be a useful tool. Did I answer your question?
Yes, he says yes.
Okay.
Okay, we have another one, the last one.
Hi. I have a question. So, why I should use this method, and can I find this method in RStudio?
Okay, so you can the algorithm we propose it is not shared yet, but we are on the stage of organizing this code to make it user friendly, and we are going to at least load that in GitHub, maybe also in our package, so you could eventually use it. It's not ready yet; it's a work in development, but you could. That's a plan for the future. And why you should use it? Well, I showed you a few examples, or at least one example, where the traditional methods for linear mixed models would not be able to handle the data. So these kind of settings, you would for sure want to use some penalized. You have a few options, but I showed some results of consistency and good properties from this algorithm. And I guess that would be the why. Of course, you always have other options, but we are having some exciting results that would be probably a good reason to use this method. Does that answer?
Yes, she says yes.
All right. Thank you all for the questions.
Thank you very much, Fernanda, for your time and for sharing this method with us. We have now another conference. Vamos a comenzar la siguiente conferencia. Tenemos el gusto de presentar al doctor Fabrizio Ruggeri. Él es doctor en estadística de la Universidad de Duke máster en estadística por la Carnegie Mellon University, matemático por la Universidad de Milano. Actualmente se desempeña como director de investigación en el Consejo Nacional de Investigación de Instituto di Matematica Applicata e Tecnologie Informatici en Milán, Italia. Es miembro electo del Instituto Internacional de Estadística y miembro de la Asociación Estadounidense de Estadística, de la Sociedad Internacional de Análisis Bayesiano y del Instituto de Estadística Matemática. Fue el primero en obtener la medalla Selner del ISBA. Su trabajo se centra en métodos bayesianos, específicamente en robustez e inferencia de procesos estadísticos. Ha realizado un trabajo innovador sobre la sensibilidad de los métodos bayesianos y antecedentes no completamente especificados. Ha trabajado en métodos bayesianos de ondas y una amplia variedad de aplicaciones en problemas industriales. Sus publicaciones incluyen más de 150 artículos arbitrados y capítulos de libros, así como 5 libros. El tema de su conferencia es Unsupervised Statistical Tools for Anomaly Detection, the Case of Healthcare Frauds. Fabricio va a dar la charla en español. Entonces, Fabricio, now you can start.